Physics Theories, Mr. Thompson here again. All right, we're moving right along. We're on page 101, and we've got Millikan's verification of Einstein. We're still working with the photoelectric effect. There's one more set of questions coming up after these notes. All right, Millikan verified Einstein's photoelectric equation using the device shown. So notice, right, the photoelectric effect is about photons incident on a cathode ejecting photoelectrons, which are simply electrons, but photoelectrons for the photoelectric effect. All right, so when the photons strike the cathode and eject electrons, how can we measure the kinetic energy of the electrons? How fast they're moving? Well, they're moving very rapidly. So the way to do that would be to indirectly do that with a voltage. And so that's how Millikan constructed his apparatus to be able to do that. It says the back voltage acts to slow down the photoelectrons, decrease their kinetic energy. So as the back voltage increases, the deeper electrons do not have enough kinetic energy to reach the other plate, but the surface electrons still do. So current decreases. If the back voltage increases until the current just becomes zero, we call it the stopping voltage, shown as V stop. Even the surface electrons have lost all of their kinetic energy by the time they reach the other plate. Okay, so there's the visual there, and you can see that this is the stopping voltage. This is a variable voltage source that can be increased, okay, to the point where the current in the ammeter drops to zero, because all the electrons, even the most kinetic, the most high energy ones with maximum kinetic energy, cannot reach the surface of the anode. All right, the equation. V stop is sufficient, barely, to reduce the surface of photoelectrons' max kinetic energy to zero. So the graph, of course, you can see as the voltage, the back voltage, becomes larger and larger, the stopping voltage, the intensity decreases eventually to zero. All right, based on conservation of energy here, in other words, kinetic energy, change in kinetic energy is equal and opposite to a change in potential energy. In other words, potential energy increases while kinetic energy decreases. You come up with this equation, Ek max equals Q V stop. Ek max is the max kinetic energy of the surface electrons in joules. Q is the magnitude of the charge of the photoelectrons in coulombs, the elementary charge. V stop is the minimum back voltage required to stop the photocurrent in volts. V stop gave Millikan a way to measure the kinetic energy, the maximum kinetic energy of the surface photoelectrons. All right, Millikan's experiment. Millikan discovered that there was a linear relationship between Ek max and F. So frequencies graphed along the horizontal axis and kinetic energy, maximum kinetic energy of the photoelectrons along the vertical axis. You can see the equation is the equation of a straight line is shown here. And you can see that the important parts of the graph are the y-intercept. That would be the negative of the work function, or its absolute value would be the work function of the material, the metal, the cathode. Frequency, if graphed along the horizontal axis, has an intercept, right, with the graph, and it's F0, F naught, the threshold frequency. The slope of the graph, the rise over the run, is equal to Planck's constant. All right, it says this verified Einstein's photoelectric equation. So you can see how y equals mx plus b, the equation of a linear line, a straight line on a graph, can be related to Ek max equals hf minus w. Or hf equals w plus Ek max, or energy of the photon is w plus Ek max. All right, we've got a few sets of questions coming up here. Well, we'll do a few of these ones on the next page to make sure you have some understanding of that. Thank you.